So today we're going to look at 3.4, which really looks at two things. One is a faster way to do division, but it only works some of the time. And the other thing we're going to look at is how can we find all the zeros, all the roots in a problem, as long as they are fractions. Okay, there's a trick to being able to find any roots, even if they're not quadratics, because quadratics we know how to do. If it's a quadratic, you use the quadratic formula, you're done. The problem comes in is, what if you have something like a cubic? How are you going to find the roots to this if you can't graph it to calculate the roots? And it doesn't look like it's easily doable with factor by grouping. Because we did do one with 4 terms at the end of class yesterday, but it was special because factor by grouping worked. So what if factor by grouping doesn't work? And what if you can't graph it? Well, there is a way to still solve it, as long as the answer can be written as a fraction. If the answer can't be written as a fraction, then no. There's no easy way for us to solve it without graphing. Okay, so we're going to look at some that have answers that are fractions. So I'll show you this trick. And then the second thing we're going to look at is synthetic division. That's the shortcut. Your book calls it Horner's algorithm. So if you see directions in the book that say use Horner's algorithm to solve, it just means synthetic division. I guess the book just calls it, maybe the person that invented it, that was his name. I'm not sure, but keep that in mind. All right, so when we're solving a problem, we can get roots that are fractions. We can get roots that are not fractions. In the homework last night, we had an answer that was something like that. I think it was like the square root of 5 halves. Well, if you type that in on a calculator, the square root of 5 over 2, square root of 5 over 2. I'm going to try one more time. Square root of 5 over 2. There we go. You get 1.5811, and it keeps going. This number, 1.58113883, you could never write that number as a fraction. It's impossible. It's not like 0.75, and you could just write it as 3 over 4, or 0.5 is 1/2. This number is not a fraction. It's like the number pi. Okay, the number pi is not, it cannot be written as a fraction. So some numbers you can write as fractions, some numbers you can't. We're going to focus on numbers that you can write as fractions. And there's a theorem that we can use to figure out the answer, as long as it's a fraction. And it's called the rational root theorem, which I'll abbreviate RRT, if we need to write that again. And when we use the rational root theorem, I'm going to go back to the steps in a minute, but here's a problem where you could use the rational root theorem. And the rational root theorem uses 2 numbers in that whole thing. It uses this number, and it uses that number. So when you graph it, if this problem is going to have an answer that can be written as a fraction, it's going to be a fraction involving the 2 numbers that I circled somehow. The -3 in the middle there doesn't matter. It doesn't have any effect on what we're going to be doing. So it's the number in front of the highest coefficient, and it's the number at the end without any variable at all. Those are the 2 numbers we have to look at and do something with them. So here's a generic example, but we're going to be focusing on that number. That's the one with the highest coefficient. And that number. That's the one at the end without any variables. Okay, so it's just written generically without any actual numbers in it. Now, To use the rational root theorem, a couple things have to happen, but I'm going to make sure that those things always happen in the problems I give you. First of all, this number at the end can't be 0. If it's 0, this theorem doesn't work. So I'm not going to give you a problem where it would be 0. The other thing is all of the numbers that I just underlined. Every number that's in front of a letter has to be something that could be written as a fraction. So if we look at this one, yes, 10 could be written as 10 over 1, negative 3 over 1, 1 over 1, negative 6 over 1. Every number in that problem could be written as a fraction. If you take something, like let's say you change the 10 to pi. Well, now you just put a number in front of x that cannot be written as a fraction. 3.14, it keeps going. It wouldn't work now. Okay? You have to have numbers in front of the variables that can be written as fractions. So those are the first two things that the problem has to meet those conditions before we can even use this theorem. So let's say you try to solve this type of problem and you get an answer that's a fraction. If you get an answer that's a fraction, that means you're going to have a number in the top and you're going to have a number in the bottom. We want to look at how you generate the number that could be in the top and how do you generate the number that could be in the bottom of your answer. Okay, this is how you do it. You start by looking at the constant. Okay. So in this problem, we would be looking at the number negative 6. And what you do with the number negative 6 is you make a list of all the factors of negative 6. Positive and negative. Every number that would divide into negative 6 without a remainder. When you figure out that list of numbers, those are the possible numbers that could be in the top of the fraction as the answer. Now we need to figure out what number would be in the bottom. I'm calling it Q. Q are all the factors of the leading coefficient. So in this problem, we would look at the number 10. We would make a list of every number that divides into 10. When you get that list, those are the possible numbers that could go in the bottom. So what you're doing with this theorem is, you might notice the way I said it, it's a list of possible numbers that could go in the bottom. You still have to figure out which one it actually is, because 10 has a lot of factors. 1, 2, 5, 10, negative 1, negative 2, negative 5, negative 10. There's lots of numbers that go into 10. We have to figure out which one actually works. But at least the rational root theorem gives us a list of things to try. Right? Otherwise, if I said to you, I'm thinking of a fraction, well, there's an infinite amount of numbers that could go in the top and the bottom. But this theorem narrows it down. So not every single number that we write down is going to work. This theorem basically generates a list of possibilities. It's still up to you to check out which ones actually work. All right, and we're gonna do that one right now. We'll go through it step by step. And we're gonna make a list of all possible. These are just possibilities. These are not actual answers, but it gives us a starting point to then find answers. Let's make a list of all possible rational zeros. So the first thing we have to do is identify the p values and the Q values. Okay, so we're going to identify the p-values and the q-values. Start with p. So p are the factors of the constant. What's the constant in that problem? Yep.
X.
No, x is a variable. Constant is something that cannot change. Yep.
Alright then, but it would be 10, 3, and...
Those are coefficients. So the constant is a term that cannot change regardless of what you plug in for the x value. Yep.
6. Negative 6.
Negative 6. So negative 6 is the constant. It's the term that cannot change no matter what you fill in for x. Negative 6 is always negative 6. So I need to know all the factors of negative 6. So what are all the numbers that divide into negative 6?
1, 2, 3, 2.
Okay, 1, 2, 3, and 6. That's half of them.
Okay. Negative 1, negative 2, negative 3, negative 6.
Yes. That's a lot of options for this kind of problem. That is quite a few. So we have 8 different options for P. Now let's do Q. Q are the factors of the leading coefficient. What's the leading coefficient in that polynomial? Yeah?
10.
10. Can you tell me all the numbers that go into 10?
That'd be 1, 2, 5, 10, like the negative versions of those.
Okay.
10.
And that's it. So, if we graph this problem, and it's going to cross the x-axis at a fraction, it has to cross the x-axis at a fraction. I'm not even saying it does, but if it does, then the number in the top of the fraction will have to be one of those 8. And the number in the bottom of the fraction will have to be one of those 8. So it basically gives us a list of fractions that we can look at and see. Now, let's list out what they are. It's a list of possible rational roots. The way I list them out, P is a number that's in the top, Q is a number that's in the bottom. Pick a P value and start with that. Let's start with 1. Let's list every single denominator that you could have when 1 is in the top. So remember, it's P over Q. So you could have 1 over 1. You could have 1 in the top, 2 in the bottom. You could have 1 in the top, 5 in the bottom. You could have 1 in the top, 10 in the bottom. That's every possible answer with a 1 in the top. Now let's list the answers with a 2 in the top. What would be the first answer that I could write down that has a 2 in the top? Yep, Lauren.
2 over 1.
2 over 1. How about the next answer? 2 over... Yep. Right, it would be 2 over 2, but we already have that one. Okay, so let's go to the next one. 2 over 5. And the next one? Yeah, 2 over 10, but I already have that, so I don't have to write it again. All right. Let's do all the options with a 3 in the top. What would be my first one? Matt?
Just 3.
Just 3 over 1. Yep, 3. The next one? Oh, Lucas.
3/2.
Good. 3/2. Sam, the next one.
3/5.
3/5. And Alexis, my last one. 3/10. I didn't have any of those. So there were no repeats. So those are all the possible fractions with a 3 in the top. Now the last one is with a 6 in the top. So Aiden, what would be my first one with a 6 in the top? Just 6. It'd just be 6/1. What would be my next one? Yep. 6/2. That's 3. We already have 3. So we don't have to write 6/2. What would be the next one after 6/2? 6/5. And the last one would be, we already have it because it would be 6/10, but that's 3/5. We already have it. Okay, so what we just did there, these numbers are very important. What these numbers represent is a list of all the fractions where this polynomial could cross the x-axis that's rational. It's a list of possible places to check. So out of infinitely many fractions, we've narrowed it down to this. These are the places where this graph could cross the x-axis at a point that's a fraction. So what we a lot of times do now is we narrow this list down. We narrow it down using the calculator. None of these numbers are that big. Like if you think of these as decimals, that's 1, 0.5, 0.2, 0.1, 0.3, 0.6, 1.5, 1 1/5, and 6. So 6 and -6 are the two biggest numbers that we have in this whole list. So if this graph is going to cross the x-axis at a fraction, we will see it in the standard window, which is from -10 to 10. It's going to have to be one of these numbers. Unfortunately, the theorem doesn't guarantee that it ever even does cross the x-axis. Or even if it does, it doesn't guarantee that it crosses at a fraction. But if it does cross at a fraction, it has to be one of those numbers. It cannot be anything else. So is there any question on that list of numbers? Yeah?
What do you do with it on there?
So now we have to narrow it down and see which ones make sense and which ones don't. Because this is just a list of possibilities. We need to narrow it. We're going to graph it. So 10 x to the 5th minus 3x squared plus x minus 6. All right, let's do zoom 6 and see what it looks like. Okay, so here's our graph. Where does it, let me double check, make sure I typed that in right. Did other people get a picture that looked like that? You did? Okay, then I probably typed it in right. I just wanted to double check. Look at where it crosses. Where does it look like it crosses? Yeah, I think it crosses pretty close to 1. So let's cross out the numbers that don't even look close to 1. Does it look like it crosses at -1? No. Does it look like it crosses at 0.5? No, it doesn't look anywhere close to that. Does it look like it crosses close to 0.2, which is 1/5? No. How about 0.1? It's pretty close to the origin. Is it near the origin where it crosses? No. Positive and -2? I mean, does it look like it's close to -2 where it crosses? No. 2/5 is 0.4. Does it look close to 0.4? What do you think, Declan? No, I'd say 0.4 is less than half. It's like over there. So no, that one doesn't look close at all. How about positive or negative 3? No. Positive or negative 1.5? What do you think, Anthony? What do you think?
Huh? Sorry, that's very
Positive or negative 1/2? 1.5?
No.
No. 3/5. What's that as a decimal?
What's that? No.
That's 3/4.
0.6.
0.6. Does it look like it's close to 0.6? Not really. It's not really close to 0.6. How about 0.3? 3/10? No. 6 or negative 6?
No.
It's not even close to that at all. Now, negative 6/5, I would say no. Positive 6/5, maybe. That's 1 1/5. That's like 1.2. If you argued that number looks close to 1.2, I could see where you could say that. 1.2, it's kind of close to it. I still think it's a lot closer to positive 1 than 1.2. But out of this list of possibilities, I would say the only ones that even look remotely like they could be right are positive 1 and positive 6/5. I don't think any of the other ones are even close. So any questions on how we narrowed that down? Thank you. So let's calculate what the root actually is. Second, calc 0. Pick a point left. Pick a point right. Do a guess. Okay. That's what we just got for a 0. Which number is that in the list? This is the number 1?
Well, close to it, right?
No, I mean exact.
No.
None of them. So where it actually crosses the x-axis is it ended up not being any number in that list at all. What kinds of numbers are in this list? These are all what kind of numbers? Fractions, which are, what do we call fractions? Yep.
Rational.
These are all rational numbers. And the number that it actually crosses the axis at is not a number in this list. So what kind of number do you think this has to be?
Irrational.
It has to be irrational. If it was rational, then it would have had to have been in that list, and it wasn't. So because we got a number for the root that's not in the list of possible rational roots, the only conclusion is this number must be irrational. What does that mean? You would have never been able to find this number without the calculator. Because it has an exponent of 5. That's way higher than a quadratic. You don't know how to work with that. The trick that I showed you to find a root that comes out as a fraction didn't work. So, in this case, the rational root theorem wasn't that helpful. But it did prove that this number is irrational. Without the rational root theorem, you couldn't have done that. So is there any questions why this number could never be written as a fraction? It's kind of an important idea, understanding why this is irrational. Yeah, this problem had quite a few options. We're not usually going to have, I don't know how many options are here, maybe 20 or so. That was a lot, including the positive and the negative for each one. It's usually a lot smaller list than that. But if you can make the list of possibilities with this one, you could probably do it for any, because it would be a lot less. All right, so we'll do another rational root problem, but we're going to tie that into this idea, which is synthetic division. So this is the last thing we're looking at for today. And again, if you're still a little unsure with the rational root theorem, it's all right. We're going to do another one. But I want to combine it with this. Okay, so like we did yesterday, what I'll do is put up a problem, and I'm going to show you the steps in synthetic division as we go. I'm just going to reword this a little bit. So I want to do this. This is the problem I want to do. Okay, don't worry about how it's worded up above. That wording is exactly the same thing as what I wrote right here. I just think the bottom one will be easier for people to understand. So, one way we could do this, we could use long division. We already know long division. Long division would work perfect on this problem. But there's a faster way to do it. It's called synthetic. The faster way works as long as you are dividing by x minus a number. So as long as the denominator can be written as x minus a number, you can use synthetic division. If the denominator has x squared or anything like that, nope, can't do it. The denominator is like 8x minus 3 halves, nope, can't do it. It has to be x minus a number for this shortcut to work. This problem is, it's x minus, and the number is 3 over 2. So the first step is to take the c value, that's the number that comes after the minus sign. In this case, the c value is 3 halves. And put the 3 halves on the outside of a bracket. And then write down all your coefficients on the inside. When you do synthetic division, you do not write any letters in the whole problem. It's all numbers. So this saves a lot of space compared to long division. Can somebody tell me what my coefficients are for each term in the numerator? Make sure you fill in zeros for anything that's missing. I'm not saying there is, but if there is, fill in a 0. Next.
2, 5, 1, 3.
2, can you say it again?
2, 5, 1, and 3.
All right, I like the 2, the 1, and the 3. What's the coefficient of the x squared?
Negative 5.
It's a negative 5. Yep. The sign to the left always goes with the number. Okay, so that's step 1. Step 2. Bring down the first coefficient. So what you're going to do is put a line like that, leave a little bit of room, and bring down the first coefficient. That's step 2. Step 3. You're going to multiply the number on the outside by the number you just brought down. Multiply 3 over 2 by 2. What do you get if you multiply 3 over 2 by 2? Okay. You get 3. Put that answer in the second column. So we multiplied 3 over 2 times 2. We got 3. Put it in the second column. And here's the big difference between long division and synthetic. Add the columns up. Yesterday we learned to subtract them. You do not subtract. You have to add them. What's negative 5 plus 3? Yep. Negative 2. Now, keep repeating that process. So let's repeat it until we're done. And then when we're done, I'll explain what the answer is based on that bottom row. So now multiply 3 over 2 times negative 2. What's 3 over 2 times negative 2? Negative what?
-3.
-3. Put that in the next column. Add those up. What's 1 plus -3? -2. What's 3 over 2 times -2? -3. And what's 3 minus 3? 0. This is the answer to the problem. So what do all those numbers mean? This side is your quotient. This side is your remainder.
Well, I was just going to say what the left side means.
Okay, so now that you know this is the quotient, can you tell me, it's going to be basically something like this. These numbers are the numbers that would go in those boxes. So can you tell me what the quotient would be?
Yeah, it would be 2x squared.
Yep.
Would you bring down the negative sign or no?
I've already put the negative right
So
there.
it'd be minus 2x
Yeah, so we can think of it that way if you want. Minus 2x,
and then minus 2.
and then minus 2. So it's 2x squared minus 2x minus 2. These three numbers are the coefficients of the quotient. This is the constant. This is the number in front of x. This is in front of x squared. The next one would be in front of x cubed. X to the fourth, x to the fifth, x to the sixth. Those are your coefficients. And 0 is the remainder. Yep.
How come when you plug -2 to where -5 is, it's not positive?
Where did you mean?
Like, oh wait, never mind. I thought it was being plugged into what the original thing was, but it's not.
Okay. So this last row, which I just put over here, the last row is the coefficients of the quotient, and the number all the way on the right is the remainder. So now, we just got a remainder of 0. Remainder of 0, that's kind of important. It tells us something. When you divide this into that, you get a remainder of 0. What does that mean about x minus 3 halves? Yeah?
It's a factor of that.
Yes, it means that x minus 3 halves is a factor. So, if you wanted to factor 2x cubed minus 5x squared, plus x plus 3, is that the original problem? Okay. That would factor into, well, one of the factors is x minus 3 halves. Now I'm telling you that x minus 3 halves is a factor of this. It's like yesterday when I said 3 is a factor of 12. How do you get the other factor if you already know one that is? Yeah?
Divide it.
You divide it. Well, we already did that. So the other factor is 2x squared minus 2x minus 2. Just like if I said to you 3 is a factor of 12. How would you figure out the other factor? Take 12, divide by 3, and you would get 4. Take this, divide by this, and you get that. That's the other factor. So now, the important thing we just did is if you had to find the zeros of this, you've turned it into a problem without any exponents that are a 3. We don't know how to work with exponents that are 3s, but we do know how to work with exponents that are 2s. We can use quadratic formula. This one is very easy on the left to find the 0. You just do this. So what would be the 0 of x minus 3 halves? Positive 3 over 2. That is one place where this graph crosses the x-axis. Does it cross anywhere else? I don't know. I'd have to use the quadratic formula, or I could try to factor that and see if there's other answers. But at least I've got it down to a problem that I can do, because it's an exponent of a 2 now. Every time you do synthetic division and you pull a factor out, the exponent here drops down 1. Yep.
I think I missed something. What are you doing there? What's that process?
To get this 2x squared minus 2x minus 2.
No, I understand. That's where you're dealing.
Oh, what's this thing called?
Yes.
This is called factoring.
No, I know, but why are you doing it?
Because originally that was part of the directions to the problem I wanted to mention earlier, but I said let's just do the division first, and I'm kind of working my way back to the original question. So if you wanted to write a problem in factored form, you have to divide by it and get that quotient. Now the key in this problem was they gave you the number 3 over 2. What if they didn't give you that number? How would you figure out the 3 over 2? Well, what kind of number is 3 over 2? It's rational. How could you generate a list of numbers that are rational that might work in this problem? Yeah?
Take the first and the last.
Yeah, what do we call that when you do the factors of those two things? That's the rational root theorem. Exactly. So in order to find this number, if they didn't give it to you, you would have to use the rational root theorem. 3 is definitely a factor of the constant. 2 is definitely a factor of the leading coefficient. And in this case, 3 over 2 worked. Now, there'd be other ones in the list. You'd have negative 3 over 2. You'd have 3 over 1, negative 3 over 1. But when you graph it, you would see that this is the only one that looks reasonable. So rational root theorem will give you this number if you need to find it. Okay, but for this one, I didn't have you use rational root theorem. I just gave you the number, pretend like someone did rational root theorem to get that number for you. All right, let's try this one. And this says to use SD as synthetic division to find the quotient and the remainder. Okay. Now, this is not x minus a number. I'm dividing by x plus 3. But could I think of it as x minus something? If I can, then I can use synthetic division. And the number that's in that box is going to go right here. Yep.
You could think of it as x minus negative 3.
Think of it as x minus negative 3. So take the number that's after the minus sign, put it on the outside. What would be my coefficients inside? Yep.
3, 7, 0, 1, and negative 11.
Good. If you forget the 0, it's going to come out wrong. You need a 0 for the x squared. Okay. And then we just go through it. Bring down the 3. What's negative 3 times 3? Yep, negative 9. Okay. Quinn, what's 7 plus negative 9?
Negative 2.
Negative 2. Okay, Brighton, negative 3 times negative 2.
Negative 6.
Negative times negative is positive, yeah. So positive 6. Eileen, what's 0 plus 6? 6. Good. Okay. Ashley, negative 3 times 6. Ashley? What's negative 3 times 6?
Negative 3 times 6.
Negative 18. 1 plus negative 18, Matt?
Negative 17.
Negative 17. And negative 3 times negative 17. What is that? Yep.
51.
51. 51 plus negative 11 is 40. Okay. What is my quotient? If it helps, you might want to do this. I don't know if that helps you, but can if you want. Yeah.
It would be 3x cubed minus 2x squared plus 6x minus 17
And my remainder?
is 40.
40. So, we basically just tried to divide by x minus minus 3. We did. That's x plus 3. What do you know, based on the remainder, about x plus 3 and the original polynomial? Yep.
It's not a factor.
Right, we know all kinds of things. X plus 3 is not a factor. Negative 3 is not a root. Negative 3 is not a 0. Negative 3 is not an x-intercept. All that list of things we learned yesterday. Nice thing about synthetic division, it always takes up a fixed amount of space. You can always fit it in a nice rectangular spot. It's not like long division, where it just keeps going down and to the right. Once you set up your two rows, you make a rectangle, everything's going to fit right there. Okay. So we want to show that 3 is not a 0. We want to show that 3 is not a root. We want to show that 3 is not an x-intercept. We want to show that what is not a factor. Yep.
Or x minus.
X minus.
Negative 3.
So we want to show this number is not a 0.
Oh, so x minus 3.
Right. We want to prove that if you plug 3 into this, you don't get 0. So what we're basically going to do to show that 3 is not a 0, we're going to show x minus 3 is not a factor, which means the same. And to show that something is not a factor, you do division, and what do you hope happens if you want to show something is not a factor? You get a remainder that's what? Not 0. So that's what we want to show here. If you divide by this and you get a remainder that's not 0, it means this is not a factor, which means this is not a root. So put the 3 on the outside. 2, 5, negative 2, negative 3. Bring down 2. 3 times 2 gives me 5 plus 6. 3 times 11. Negative 2 plus 33. This isn't looking like we're going to get 0. 3 times 31.
93.
And 93 plus negative 3. 90. We got a remainder of 90 when we divided this. That means x minus 3 is not a factor because it had a remainder. Because x minus 3 is not a factor, 3 is not a 0. 3 is not a root. 3 is not an x-intercept. All means the same thing. Any question on that? All right, so we go down to the last 2. That one. Okay, so let's try a full problem now that involves synthetic division and the rational root theorem. So it's going to be what we just did, but they're not going to give you the number to try. You have to figure out the number yourself. So the strategies for this kind of problem is use the rational root theorem, use the graphing calculator to narrow that list down, just like we did on the first problem. Once you've narrowed it down, find a number that works and use synthetic division to divide. Remember, the reason why we want to do synthetic division is because when you divide through synthetically, you take the exponent that you started with, which was a 3, and it gets smaller and turns into a 2. If we can turn things into exponents of 2, then we can use quadratic formula. You cannot use quadratic formula on something with a 3. So we have to find a number that's going to work with the rational root theorem. If you can't, then you're stuck. You're not going to be able to do it. So I guarantee you, there is a number that will work in this problem. So let's start by making a list of numbers. X cubed minus 3x minus 2. If you want to put a 1 there, you can. What are the factors of negative 2? Numbers divide into negative 2. Yep.
Plus or minus 1 and plus or minus 2.
Okay, not that many options. Plus or minus 1, plus or minus 2. Q are the factors of this number in front. What number is going to 1 without a remainder? Plus or minus 1. Again, not that many options. So let's make a list. These are possible, rational roots. Not going to have as many numbers as the first problem we did. Can somebody tell me what are all my possible rational roots I could have? These are all the places this problem could cross the x-axis at a number that's a fraction. Yep.
1 and 2.
What else?
1 and 2, and then negative 1.
Okay, there are 4 options. 1, negative 1, 2, negative 2. Let's graph it. And we want to find one that works. I do not want to waste time doing synthetic division on a number that doesn't work. Okay? I want to find one of these 4 numbers that works. And I know one of them is going to work because I wouldn't be asking you to solve the problem if none of them worked. So none of them worked on the very first problem we did today, but one of them will work here. If more than one of them works, great. Pick any one you want. So out of that list of possible rational roots, which ones look reasonable? I think there are more than one. Yep.
Negative 1 and positive 2.
Negative 1 and positive 2, and I know they both work because if you did second calc 0, you would get those 2 numbers. Let's pick one. Let's do 2. So let's put the number 2 on the outside and put our coefficients on the inside. 1, 0, negative 3, negative 2. If you get a remainder here that's not 0, start over. You picked the wrong one. But hopefully if you've gotten to this point, you're not wasting time because you looked at the graph and you already know that it's going to be that. You would have done second calc 0 to check. Okay, so we're checking 2. Bring down the 1. What's 2 times 1? 2. 0 plus 2? 2 times 2? 3, negative 3 plus 4. 2 times 1? And negative 2 plus 2? 0. So now we know something. We know that 2 is definitely a root to this problem. Now, we're done with looking at this x cubed minus 3x minus 2. Now, you look at this. That's the problem you're going to work with for the rest of this now. How would you write this out? What does that mean? Yep, go ahead.
X squared plus 2x plus 1.
X squared plus 2x plus 1. You're done with the original problem. Look at the quotient now and set that equal to 0 and continue solving. But now the exponent is a 2. Before, it was a 3. We can work with exponents of 2. We can try to factor that. If we couldn't, I'd do quadratic formula. What would be my first 2 terms in each set of parentheses? Yep.
It would just be x plus 1.
X and what?
Oh, I can't remember what it is. X plus 1.
Okay, so you said x plus 1, and what's the other one?
X plus 1.
X plus 1. Let's check it. X squared plus x That's plus 2x. And 1 times 1 is 1. So now, set each of these equal to 0 and solve. What do you get when you solve the first one?
Negative 1.
-1. What do you get when you solve the second one?
Negative 1.
-1. We have the same answer twice. You don't have to write it twice. You only have to write it once. So -1 is the other root. So 2 is a root, and -1 was a root. And if you go back up and look at the graph, that looks exactly like what's happening. 2 and -1. Now, sometimes what's going to happen is you're going to get to this step, and you are not going to be able to factor it as nicely as this. What would you have to do if this problem wasn't factorable? Yep.
You just try the other possible root. Do a synthetic division.
Well, if you've gotten to this step, then you already found a root that worked. So this root was correct. But let's say we got to this step, we tried 2, it worked because we got a remainder of 0, but now we have a quadratic equation that we can't factor. How are we going to solve this? We want to continue from this step, though. We don't want to go back at this point. Yep.
Long division?
No, because it's a quadratic. So we have a method of solving problems that have exponents of 2. Factoring is one way, but let's say it didn't work. Yep.
Quadratic formula.
You're going to have to use the quadratic formula at this point. And the calculator can't do the quadratic formula for you. If you try to calculate a 0 at an answer you need the quadratic formula for, you're just going to get this huge decimal at the bottom. On a problem where you need quadratic formula, you want the answer to look something like, I don't know, I'm just making that up. But that's what your answer should look like in a quadratic formula problem. So you have a number, plus or minus, and then a square root, and then another number in the bottom. The calculator can't give you numbers that look like this. I'm going to want something that looks like that, if you can't factor it. Okay, so you have to use quadratic formula. Again, I just made this up. That has nothing to do with this problem. Any question on that? Okay, so you'll get to some in the homework where you will find a rational root. You'll divide by it and get 0, and it'll work. Then you're going to get to this step in red, but it's going to be a quadratic that you can't factor. So you're going to have to use quadratic formula. Okay, so those are the problems for tonight. So it's like 11 questions, 1, 2, 5, 6, 9, 10, 13, 14, 17, 18, and 27. So we'll look at those tomorrow, and then we'll look at 3.5. Okay, so we'll look at 3.5 tomorrow.